travels at a constant speed. Is that true? The speed of light is constant.
No.
It is.
Why not?
It is constant, but the space could be bent.
But what?
But the space could be bent.
Oh, space could be bent. Yeah, that's general relativity. Einstein's theory of gravitation says that large masses bend space.
Well, light is always determined, light depends how we look at it.
Right. But you know, you hear this thing that the speed of light is constant, sometimes represented by the constant c for constant, right?
Mm-hmm.
However, they leave out an important phrase when they say this. The speed of light in a vacuum is constant. If light is traveling through a medium, that medium will slow down the light. Actually, what happens is very complicated. You know, I suppose the light somehow interacts with stuff around it. You know, it's a little bundle of energy, right? A photon. A massless bundle of energy. But the speed of light in a medium slows down, and so the denser the medium, the slower the speed of light, right? They say the speed of light in a vacuum is constant, but if the light's there, then it's not a vacuum. So it's like a contradiction in terms, isn't it? Plus, what's a vacuum?
It's supposed to have like nothing in it, like even space itself is supposed to be fluid, I think. So it's not even supposed to have space in it.
It doesn't even have space. Yeah, right. Well, supposedly a vacuum is space with nothing in it. Although, if that space is in the universe, then things are always popping in and out. Even though there might be nothing there, things can just pop out of nothing. Yeah. Particles and antiparticles pop out at the same time. And of course, if you're at the event horizon of a black hole and a particle, antiparticle pops out of nothingness, then one of those two could get trapped inside the black hole and the other one escape. So the stuff that escapes is called Hawking radiation, after Stephen Hawking, who discovered it. And supposedly it's a real thing, I don't know. Yeah, a lot of this stuff is pretty bizarre. Yeah, so the speed of light in a medium changes, and the velocity of light in the medium depends upon the density of the medium. So the light travels faster through air than through water, and that's, you know, Snell's law is described here in number 57, and we extend that further in number 58. In number 59, they've got the phases of the moon. It says, as the moon revolves around the earth, we've talked about the earth revolving around the sun, but at the same time, the moon is revolving around the earth. The side that faces the earth is usually just partially illuminated by the sun. So the phases of the moon describe how much the surface appears to be in sunlight. An astronomical measure of the phase is given by the fraction f of the lunar disk that is lit. When the angle between the sun, earth, and moon is between 0 and 360 degrees, then the fraction is given by f equals 1/2 1 minus cosine theta, where theta is what? Theta is the angle between the sun, the earth, and the moon. Okay, so let's say here's the sun. Think of that as a single point. And up here's the earth and the moon, right? So now that forms a triangle, right? So which one of these is theta?
Would it be like the angle where the sun is at?
That wouldn't vary so much, right? They're saying that theta should range between 0 and 360 degrees. So which one of these angles? So think about the moon going around the Earth, right? For a stationary Earth, let's say, the moon trying to go, of course the Earth is moving at the same time, so, but we can sort of imagine that this distance is relatively constant, so it's, you know, this orbit here, that angle is going to go between 0 and 360, right? So we can think of this angle, I think, as being our theta, right? And if you think about, you know, standing on the Earth and looking at the moon, when the moon is over here, you're going to see much more lit than when the moon is between the Earth and the sun, right? That would be the dark of the moon. Then the other side of the moon is lit.
Dark side.
But, yeah. The other weird thing is that the moon's face, the face of the moon pointing the Earth is always the same, right? So as the Earth goes around, as the moon goes around the Earth, it's always showing the same face to the Earth, but we'll see only some of that be lit, right? And so in a new moon, it's when the moon is here, and a full moon, it's when the moon is over there. You might say, well, that should be an eclipse because the Earth is between the, yeah, not exactly, right? Only sometimes. But yeah, so I think we're going to figure out. So what's their question here? This is number 59. So determine the angles theta that corresponds to these phases. F equals 1. Oh, F equals 0. And this is the new moon. That means that the moon is totally dark, so you'd be here, right? Looking at the Earth, on the Earth, looking at the moon, you'd see just the shadow face. But the entire face would be in shadow. Okay, so that would say, well, 1/2 1 minus cosine theta is equal to 0. We can use the zero product principle and say, well, this is exactly the same as cosine theta equals 1. Where is that? Theta must be some multiple of 2 pi. Or some multiple of 360 degrees. Sometimes you see it like that, right? So k times 360 degrees, if you're writing in degrees. But how about the quarter moon? Is that the other? Yeah, a crescent moon. So the crescent. So this is the new moon, right? And here we'll have the crescent moon. And in that case, we have F equals a quarter. Is that right? Yeah. Right. And so for that, we'll have 1/2 1 minus cosine theta equals a quarter, which says that 1 minus cosine theta is equal to 1/2, which says that cosine theta is equal to 1/2, right? 1 minus 1/2 is 1/2. And where does that happen? I'm dialing up on the circle. And we want the x-coordinate to be 1/2. That's going to happen at pi over 3 or negative pi over 3, right? Or perhaps we think of this as, if we're thinking between 0 and 2 pi, then this would be, where are we? Well, 2 pi is 6 pi over 3. So if we subtract pi over 3 from 6 pi over 3, we end up here at 5 pi over 3. So that would be this positive angle like that, right? So we have these two angles where the cosine is equal to 1/2. This is 1. And those are well-known benchmark places. And so theta would then be, you know, I prefer to think of it as plus or minus pi over 3. But if you want angles between 0 and 2 pi, you'd say pi over 3 or 5 pi over 3, right? Which is negative pi over 3 plus 2 pi. In terms of degrees, 60 degrees or 300 degrees, right? And that's the crescent moon. Does that seem right? Yeah, I guess so. So I don't know where are we forming theta? Maybe we should be forming theta over here, right? With a positive polar angle. In which case we'd see the crescent moon about here and here, right? Huh. Okay. So it seems like that would be closer to the full moon, so it'd be more like 3/4 than 1/4. So maybe we're measuring it here, and it's just a little bit unusual for my way of thinking of things. But yeah. So I guess we would be measuring clockwise from that position, right? Or 5/3. Never mind, what a mess. Okay, let's get into more trigonometric equations, which I love it when the next section in the chapter, they have a whole new section. It's just more of what we were just doing. So why separate them? Well, it gets a little more complicated.